Hello. Today we will be introducing the Mandelbrot set. The Mandelbrot set is a collection of points which converge in the complex plane for a certain iteration of the Mandelbrot polynomial. The polynomial is given on screen. Mapping the collection of converging points gives this image. We call this a fractal, which was given its name by its discoverer Benoit Mandelbrot. It is generated by taking multiple C inputs and iterating the Mandelbrot polynomial for large n. The spaces around the yellow lines correspond to areas which contain divergent points, though this varies for different values of n as seen here. The red area is the collection of convergent points for the respective iteration n. As we increase n, the red area becomes smaller and has a more accurately defined edge. The colours also take a range, where colours closer to blue represent points that diverge at smaller iterations. The edge of the fractal is called its boundary. The boundary is made from a collection of fixed iterated points. Take c to be -2 and z0 to be 0, for example. The iteration of z would be z0 equals 0, z1 equals -2, z2 equals 2, z3 equals 2, and finally zn equals 2. Points with this property make up the branch tips, centres of spirals, and the points where branches meet. The Mandelbrot set has a few unique properties, the most important of which are self-similarity and chaos. Firstly, let's talk about self-similarity. The Mandelbrot set is self-similar, illustrated by the fractal image repeating at smaller scales. We can see this in the animation shown here. Now let's talk about chaos. A system is chaotic if it lacks any predictability. If we take a range of values for c and determine whether they diverge, the convergent points may be plotted against the respective c values. This creates an image which we call a bifurcation diagram. The diagram is well ordered initially, but then becomes noticeably random towards the end. This shows its chaotic nature, as it is impossible to predict when the image will become unordered. The Mandelbrot set may be changed to a higher order polynomial. This gives a formula for the generalized Mandelbrot set. Here is a plot for the example given. Notice that there are 4 cusps. Generally, the number of cusps is given by k minus 1. Here are the plots for the k values 4, 5, 6, and 7. As k approaches infinity, the plot will approach the unit disk. Now let's move on to other related sets. The Julia set is created using the same iterative process as the Mandelbrot set, though here we fix c and vary the starting point of the iteration. Much like the Mandelbrot set, the Julia sets are self-similar. Here are some of the examples of Julia set fractals that we have created. Thank you for watching.